Okay. Hey everyone. So I decided to start this session with a review of latent and sensible heat transfer, just because I think of all of the concepts this week, this is the one that tends to be um, people get the wrong more often than anything else, because I think it's not quite as intuitive as some of the other content anyway. So I want to go over that and give you a little demonstration of it. Hopefully this will help, um, sort of codify things in your mind. So if you remember, sensible heat transfer is when you transfer heat and it results in a change in temperature, right? So anytime heat is transferred and there's a change in temperature, right? So if I have like a cold glass of water, I put my hand against it, my hand gets colder, and the glass gets warmer. So there's a change in temperature, so that means it's sensible heat transfer. Okay, that's really easy to remember, really straightforward. So latent heat, on the other hand, find my cursor, here we go. So latent heat is when you transfer heat from one place to another, but there's no temperature change, but there is a phase change. Okay, so when there's heat transferred, that means there's an energy transfer, which means something has to happen, right? So if it's not a change in temperature, what happens is it changes the phase. So it goes from either, solid to liquid, liquid to solid, liquid to gas, gas to liquid, or you can even go from gas to solid, or my personal favorite, solid to gas, which is called sublimation. That's something where you have a solid that just goes and like sublimates into gas, and it's really rare, but it actually does happen, particularly in meteorology. But anyway, so if heat is transferred either to or from a substance, something has to happen. Okay, so either the temperature changes or the phase will change. Okay, so the with latent heat, remember that the phase changes, but there's also no temperature change. I'm gonna show you, like demonstrate an example of that here in a minute. But anytime you do this, there is heat moving around. So for water, the latent heat of vaporization is the amount of energy that's required to either vaporize 1 pound of liquid water into steam, or to condense 1 pound of steam into liquid water. And I'm going to show you an example of this here in a minute. But the thing about latent heat is that it tends to be a lot more than, like it depends to be a lot of heat, right? So, and I'll show you an example of this in a minute. This is really important for HVAC, right? So all our air conditioner, refrigerator, freezer, heat pump, etc., they all use this latent heat process to cool and heat buildings. And we'll talk about that in more detail later when we do HVAC. Okay, so the really important thing to remember, and I want to stress this, is that to go from a solid to a liquid, you must add heat to the substance. Okay, so if it's water, right, so to melt ice, you have to add heat. Pretty intuitive. And then to vaporize liquid water, you have to add heat. But that part I think is pretty easy to remember, but you have to remember that the opposite is true as well. That when you go from condense from a vapor to a liquid, you dump that heat out of that steam or whatever that is, whatever gas, whatever substance it is. When you go from liquid to solid, so when you freeze something, you release a bunch of extra heat. Okay, so that's really important to remember. And different substances have different latent heat of vaporization and fusions. So, obviously in the HVAC equipment and air conditioning, we don't use water as a refrigerant. There's other chemicals that we use for that. And they each have their own specific latent heat of vaporization, latent heat of fusion, and they vaporize and they freeze and melt at different temperatures depending on the pressure. So there's all kinds of other factors that are at play. But the key thing to remember is that when you go from solid to liquid or liquid to gas, most importantly, liquid to gas, because that's what's happening in refrigeration systems. Liquid to gas requires adding heat to the refrigerant, and gas to liquid dumps heat out. Okay, so it releases heat. So let me show you an example And I think helps illustrate how this whole latent heat thing works. So let me see if I get my pen here. Right, so let's say we have 1 pound of water here and 1 pound of water over here. Okay. Okay, so if I have 1 pound of water and I'm currently at 209 degrees Fahrenheit, which phase am I, solid, liquid, or gas? So at this point, remember the boiling point of water is 212 degrees Fahrenheit, and the freezing point is 32 degrees Fahrenheit. Sorry, my camera's in the way. Okay, so we're at 212, we're not boiling yet. So we're still at a liquid, right? So if we add 1 BTU, remember that's defined as a BTU is the amount of energy required to heat up 1 pound of water, 1 degree Fahrenheit. Okay, so if we add 1 BTU to 1 pound of water at 209, we're going to go up to 210 Fahrenheit. We're not yet at our boiling point, so we're still a liquid. So we can add another one. We go to 211, we're still a liquid. We add another one, we're at 212. Now here's the key. At 212 degrees, as soon as we reach 212, we are still technically a liquid. Okay, so we're actually what's called a superheated liquid at this point. We have not yet boiled. If we just right at that point of 212 degrees and we don't add any more BTUs, we're still in liquid. Now, if we want to go to a gas, if we want to vaporize this whole thing, okay, so if we want to make that whole pound of gas, we have to add 970 BTUs to it, okay? But when we do that, we're still at 212 degrees Fahrenheit, okay? So we add all of this heat, a whole bunch of heat, okay, 970 BTUs of heat, and we're still at 212 degrees, okay? But we vaporize. So from here to here, because we've changed the phase, this is latent, right? Because the latent, we go from liquid to gas, but there's no temperature change, okay? But all the way from here to here, right? This is all sensible because we stayed in the same phase, right? And throughout we've changed the temperature, okay? So the temperature changes, phase doesn't, that's sensible. And then from here to here, the temperature changes, stayed the same, but the phase changed, so that's latent, okay? And then we can go in the opposite direction as well, right? So over here we have 1 pound of liquid water, right? So we're at 36 degrees. We remove 1 BTU, we drop to 35. We're still a liquid. Let's just drop 3 more BTUs out here. We're down to 32, but we're still a liquid, okay? Just like with boiling, right when we reach our freezing point, we're actually still a liquid, or just a super cold liquid. And then we have to remove 144 BTUs to go to a solid, but we're still at 32 degrees, okay? So from here to here, this is your latent heat. Everything else above it is sensible because, again, temperature change, phase is the same, that's sensible. Temperature same, phase changes, that's latent, okay? And then we could go in the opposite direction as well. So if we took, in this situation, if we boiled it, so we have 1 pound of steam, okay? And if we would cool that down, okay, we would have to, if we wanted to condense all of that into 1 pound of liquid water at 212 degrees, we would release 970 BTUs, okay? So we take the steam and we condense it into liquid, and we're gonna dump this 970 BTUs back out, right? So thermodynamics, right? So energy is never created or destroyed. So if you add heat to something to vaporize it and it changes the phase, when you change it back to the original phase, it's gonna dump it back out. And that's fundamentally how all of our air conditioning equipment works and refrigerator works, right? So a refrigerator takes heat from inside the refrigerator and dumps it outside. An air conditioner, if you're cooling the house, it's going to take heat from inside the house and dump it outside the house. And again, we'll go over that in a little more detail later, but I did go over that, the basic vapor compression refrigeration cycle in another video. So feel free to go ahead and review that if you want to. And just to show you that this, how this works, share my screen over here. Let me show you a little demonstration of this to show you that it does, how it actually does work. So here's,
Okay, for this video we are going to demonstrate what happens to the temperature of liquid water when we bring it to its boiling point. So I have a hot plate which is red hot, ready to go, and I'm going to put on a beaker of water that has a thermometer in it. It's above room temperature to move this demonstration along a little bit.
okay, so you can see here, this is sped up, and you can see the temperature of the water going up. Okay, so it may be hard for you to see, but we're at centigrade, we're at 60 degrees, so we're at 140 degrees Fahrenheit. And this is the world's least exciting video, at least the first part. So I'm just gonna speed it up a little bit here. Okay, so we're warming up, getting hotter and hotter and hotter. We're at about 190 degrees, about 200. So you can see it is starting to vaporize just a little bit. Okay, so now we're at the boiling point.
Okay, and now we've reached the boiling point of water. Due to our imperfect thermometer, and maybe due to some things dissolved in the water, our boiling point is above 100 degrees, but let's see what happens to the temperature.
That's 100
as
Celsius.
This continues and as we add more heat to the water, and let this demonstration run.
So the point here is that it's at the boiling point. Water's boiling away, so it's changing its phase. Okay, but you notice this thermometer, the temperature is not changing at all, even though we're dumping a whole bunch of heat into the water, right? To keep dumping more and more and more. That dumping of heat into the liquid water, that's that heat that I showed you in the chart that contributes to the latent heat of vaporization. So when you dump the heat into the water, you see the temperature is not changing at all, not changing at all, but it's converting it to steam. And so that heat, again, first law of thermodynamics, has to go somewhere. And what it does is it stays with that steam. Okay, so then if you can, I mean, this just goes, it just keeps going and going. So feel free to watch the rest of the video on your own time, but I assure you nothing else exciting happens. So I'm gonna stop the video and go back to my screen here. So what that's I think a pretty good demonstration of this phenomenon, that you're dumping a bunch of heat into this liquid, but it's not changing the temperature, which to most people would be counterintuitive. It's like, well, how is it possible that the water is not getting any warmer? But that's what happens when you boil water. So when you cook something and you boil it, it gets to 212 degrees or thereabouts, depending on the purity of water. And if you're higher elevation, it boils at a lower temperature, which is why you have to cook pasta longer at higher elevation. But it stays at that temperature the whole time that it's boiling. So if the water's boiling, it's 212 degrees, give or take a few degrees, depending on a few other factors. Okay, so that's, I think, a pretty good example of latent heat. So hopefully that helps you sort of wrap your mind around what latent heat is, and some of the, the basics of latent heat. So again, we'll dig into that in a little more detail later on when we do HVAC. But it's really important that you understand that fundamental process, that when you vaporize something, you add heat to it. The heat stays with the vapor. And then if you condense the vapor back into a liquid, that it's going to release that heat back out. Okay, so that's just a really essential thing to understand. Okay, so the other thing, I did want to go over, I'm not going to spend a whole lot of time on going over these because you can read these on your own. But I do encourage everyone. Let's go to my cursor here. Here we go. To look at these different sustainable building types, you all did a really good analysis overall, and found some good examples of each. So I do suggest you go through these. What I'll do briefly is just give you like a quick overview of the different types. I'll just go down the discussion board list. So net zero energy homes, really all a net zero home is it's a home, it's a building that produces just as much energy as it uses over the course of 1 year. They're going to be all electric. Usually they have solar, but they could be any type of renewable technology. Could be wind, could be geothermal, could be small hydro if they have that available to them. But the key to a net zero home is that if you take all of the electricity they use over the course of 1 year, and then you total up all of the energy that they generated on site using renewable sources. So you can't use like a generator, a diesel generator or a natural gas generator. That wouldn't qualify. It has to be renewable energy. And if that balances out, okay, so it doesn't matter when you generate, when you use, as long as it balances out over the course of the year, that's net zero. So this is a pretty common concept now. 10 years ago, it was pretty rare to find a net zero home, but now you can find them all over the place. And there are certain municipalities that are building to net zero standards. I know I'd have to look it up, but I know Delaware has a policy. I feel like by the mid 2020s that all residential buildings have to be net zero capable. I'd have to look that up, but for those of you, and I think everyone is in the construction management field, you're going to be dealing with net zero probably at some point in your career if you get into the career field now, because a lot of net zero, there's not a lot of net zero policies being passed, different states, different municipalities and so forth. So this is really an important concept to be aware of. So it's definitely worth looking into. So straw bales, it's kind of a more niche application, I guess you could say, pretty uncommon. But there are straw bale houses out there, and what the straw bale is, here's a pretty good image here where you can see the straw bale on the walls. So what it does is it helps, it basically provides insulation, thermal mass to your building. It doesn't provide structure, you still need framing, but it's a natural material. The idea here is that instead of using all of these chemical laden, insulation and like, all of the engineered framing members and, OSB and plywood and all that stuff, that even though they're natural products, they do have some artificial elements to them, right? So they have your glues and chemical treatments and so forth. So it's considered a natural building technique. It's a really good insulator, good sound attenuator. It can be used, built with local materials as well. It's a nice picture. It's a cool straw bale with a nice green roof. Really interesting. A lot of these will be hybrid homes. Will be like straw bale and cob. So LEED. LEED, there's a number of different LEED certifications. So this LEED is LEED for Cities and Communities, which helps. It's basically a certain, LEED. Most of the LEED design that people are aware of are for buildings or homes, right? So you can have your LEED certified, your LEED silver, gold, or platinum. And so that's where most people are used to thinking about. And that's all these, it's a rating system that integrates all different aspects of sustainability, from water reduction to renewable energy to energy efficiency to the use of non-toxic products to use of local materials. There's a whole huge spreadsheet that lists all of the different characteristics of LEED. And again, this is something that's really common in the construction field. So if you're in construction management, you're going to encounter LEED buildings at some point. But LEED for Communities is like LEED for a bigger scale, where they actually look at the more community scale impacts of the design, right? So it's meant to sort of develop more sustainable communities. You can see that there's all these different categories. So you want to have natural systems, so not, you want to preserve green space as much as possible and minimize your environmental damage. You want to have transportation available for everyone, so equitable transportation, um, a lot of public transportation, but also like designing connected networks. So you have like transit oriented development where you have bike paths that are connected to bus routes, which are connected to light rail, which are connected to, a regional rail, whatever. So that's a really important part of having a sustainable community, promoting a community where people can live with minimal car use. Um, so water efficiency, that includes, stormwater management, but also, not using a lot of water in general. So you look at your energy and your greenhouse gas emissions, the materials. So what kind of materials are you using, the overall quality of life. And also you want to have everything like regionally and locally connected. Okay, so you should have sort of this unique community feel, um, and promote a more sustainable lifestyle using renewable energy, minimizing your impact on the environment, making it equitable for everyone, having affordable housing, having affordable transportation, and so forth. So this is a really pretty robust um, certification. Um, and here's the Hearst Tower in New York City. That's a cool building. Okay. Then we have Passive House, which is rebranded as Passive House. So there is a Passive House standard. And now it's the North American version is Passive House. So a Passive House, really the concept, the main concept behind Passive House is that it's a building that can be sort of naturally heated and cooled. That's really the bottom line, as opposed to, so they sort of passively think of the term passive means like you don't have to actively heat and cool very much, if at all. Okay. And so that it's going to require the use of some renewable energy. There's a lot of passive house strategies that don't involve energy generation though. So a big part of passive design is actually not having to generate your own energy. And so things like south facing windows where you can capture the sun in the winter is a really important one. You design the house to, if you need to cool it in the summer, you orient the house just so that it can capture the prevailing wind and sort of can cool the house naturally. Use things like thermal mass, which help. This is a passive design element that maybe we'll go over in a little more detail at a later time. But passive design elements don't actively generate. They're not active. They're just, the sun is heating things up, the wind's cooling cooling it down, and so forth. And so they are specific to the climate. You have to be really careful about how you design the house, how you orient it, what materials you use for it, and so forth. And they're also going to be super efficient, super tight. So a certified passive house is going to be really, really tight. Okay, so you have to make sure all of, thinking back to our building construction, all of our very tightly sealed, top plate and the sill plate and the bottom plate, all the framing members are going to have to be really, really airtight. So a passive house will be so tight that you actually have to provide active ventilation in order to provide enough fresh air for the people inside. That's how tight these buildings are. They're incredibly tight. Also have a lot of insulation. So again, the key here is that you don't want to have to heat or cool it at all if possible. You're really just letting the elements keep it comfortable. That's a nice, interesting design. Okay, so living buildings. So this is, in my experience, the most robust certification out there. In order to become a true living building, I mean, you have to satisfy every single aspect of the living building challenge matrix. So with LEED, you can sort of pick and choose a lot of the things that you do. Whereas with living buildings, you have to do every single one of these, and they're very robust. Net zero water, net zero energy. You have to have promote equity. There are certain products that you can't use. There's a red list, quote unquote, red list of products. You look at your carbon footprint and you have to, any land that you use, you have to set aside an equal amount of land in perpetuity. So there's all kinds of really, really, really robust metrics here. I think probably one of the hardest ones is the net zero water. So just like with net zero energy, you have to generate as much energy, renewable energy, as you use in a year. With net zero water, you have to capture as much water as you use over the course of a year. So, you're going to have rainwater catchment systems. You're going to have gray water systems. I mean, this is a really, really robust certification. So this is not as common. There's not nearly as many living buildings in the world as there are LEED, or certainly as LEED. But it's really tough to get this. Another really important aspect of this is with LEED, you get your LEED certification before you really start using the building. That's how you design it. With living buildings, you don't get the certification until at least 1 year after you live in it, to prove that you're actually net zero and everything. So it's a really robust one. Then we have earth ships. So this one I'm less familiar with, but they tend to use a lot of as Brian put in here, upcycled material. So you'll use things like old car tires for walls, and you can use, so here's your 6 main design principles. So natural upcycled materials. Okay. You can use adobe, old tires, thermal, solar heating, cooling. So that's kind of your passive design systems. Okay. So you have earthen walls is really common. Must have renewable energy. Okay. Water harvesting must be there. Contains sewage system according to botanical. Okay, so you have gray water systems, okay, which are basically recycling of, so gray water, if you're not familiar with gray water, is household water that's not, it's not sewage, it's not your toilet water. It's like your water that you use to wash dishes or shower or take a bath, right? So like that is not contaminated to the point that you can't reuse it. So gray water systems will reuse that type of water, whereas black water is the sewage, which you're not. Although there are ways to do, believe it or not, you can make something called humanure. It's just a real thing. You can get like a composting toilet, which is really just sawdust. Anyway, so gray water systems, food production, so you have to produce a lot of your own food. Yep. So this is a pretty loose, I don't know that there's a certification per se, but it's sort of a style of building. So this is, that's really cool. So lots of solar here. I'm sure this is south facing roof, growing a lot of their own food. You can see it like really fits nice and seamlessly into the natural environment. Yeah, really cool. And we have Energy Star qualified homes. So this is something that you can get, anybody can shoot for. And there's a whole rating system. And I forget what it goes from until, but you can see the scale down here. And so this is basically, it's energy only, okay? So it reduces your energy use. So it's cheaper to operate these types of buildings. But in addition, we're reducing anytime we can reduce our energy use, we reduce our environmental impact and sort of, save energy for other people. Yep. So Energy Star can be really any style. It just has to be basically an efficient home. So you got all these cool things: low E windows, R34, R66 ceiling. Yep. Yeah, passive solar. Yeah. So that's one that's not super common, but a lot of people know about it. Then we have LEED Homes, which is this is the one where you have your whole rating system, right? So I'm sure a lot of you are familiar with LEED. If not, you should make yourself familiar with it, because it is something that's used a lot in the construction industry. So normally the class that I'm teaching now, I teach in the, if you're familiar with the Stanton campus, the Sustainable Energy Training Center, the new energy building, the solar panels on top. kind of that sloped roof, AKA the G wing. That's actually a LEED gold building. And so it's pretty common to see LEED buildings all over the place. So there's a whole rating system, and you basically, in the design process, you go through and you figure out, okay, how many points can I get by, doing low flow fixtures and adding bike racks and putting in solar panels and connecting your building to the local transportation network. There's a whole bunch of different ways to get points. And then you add up your points and you get, there's 4 certification levels. There's right here, yeah, certified, silver, gold, and platinum. Okay, so platinum's the highest. And so there's all kinds of LEED buildings all over the place, and you can search their website. And this is not a one size fits all certification. There's just many, many different kinds of LEED buildings out there. That's a good example. We got some geothermal heating and cooling, some passive cooling, water conservation, so water catchment, renewable energy, all these things. Anyway, this is something that is pretty common in the industry, so definitely worth checking out. There's also jobs, you can be a LEED AP. Basically, you're someone that is an expert in LEED rating systems, and you can work hand in hand with architects and builders and homeowners, designers, to help them design their LEED buildings, and you sort of certify their points and so forth. That's something that actually it's not an easy certification to get, but it's someone with some experience and preparation, it's not that bad. Then we have neighborhood development, which is really similar to, did we do this before? Yeah, so this is basically designing smart neighborhoods. So you can see green infrastructure, wildlife habitat protection, great streets, sustainable characteristics. So this is like LEED buildings, but for neighborhood design. Yep. So that's a good point. So homes and other buildings cannot be truly sustainable unless they exist within a high quality and compact neighborhood context. So again, in construction management, this is something you could encounter. You definitely need to start going more toward smart growth, new urbanism, if you're familiar with any of those concepts. But where you have really good connectivity and the whole community is sort of planned out all at once, right? So you're planning the transportation along with the buildings, along with schools, along with the social life, along with everything. And you try to minimize the need for automobile use, maximize the opportunities for pedestrian traffic and community interaction and staying locally and so forth. So this is a really, new urbanism is maybe 20, 25 years old, give or take. And it, unfortunately, not enough neighborhoods are designed this way, especially in Delaware. They just slap neighborhoods up around here, throw up a couple of plazas, and have single use, and they pretty much force you to drive everywhere. The building design and construction, so kind of more of the same here. We have Cob Houses. So Cob is a really interesting application. So it's a mixture of sand, straw, and clay. So clay is a really important element of this. And so it's all natural building materials you can use locally. These are some pretty good pictures. One of the cool things about Cob is that it's made mostly of clay, so you can shape it any shape you want. And you can build it with local materials. Speaking from where I am in North Wilmington, we could build Cob houses all day, every day, because there's just clay all over the place in the soil up here. And so it's a natural building material. It's a natural thermal mass. So it really is good at sort of storing heat. And also, if you make the Cob walls thick enough, in a really, really hot climate, it will take a long time for the walls to heat up, for the sun to sort of heat the walls up all the way through. And so this is good for pretty much any climate. But natural earthen materials are a good wall construction material for, you think about like the desert Southwest where they had adobe and so forth. I mean, if you make the walls thick enough, you don't need to have much cooling because it takes so long for them to heat up. It's a huge thermal mass. So yeah, cob buildings are pretty cool. There's not a whole lot of them out there. It's not real common, but there is, you can build cob ovens, for example, which is a little bit more, down to earth, I guess you could say. But there are definitely some really interesting houses out here and some good pictures there. Then we have the sustainable city in the UAE. Okay, so this is a relatively new project in the United Arab Emirates. And the goal is really to have a city run 100% on renewable energy. I'm not super duper familiar with this, but the idea is to create a city that's, and this is in the United Arab Emirates. So they'll grow a lot of their own food. They're trying to generate all of their electricity from renewables, which is interesting considering the UAE is a major, all their money is oil, or almost all their money comes from oil. But they kind of see the writing on the wall, and they know that the era of oil is going to come to a close someday. And not only do they have a lot of oil, but they're, in the Middle East, so they have a huge solar resource there. And so they're taking advantage of that to build this sustainable city. So it's something worth looking into. And I think they hope to build a model that can be sort of used in other places. Okay, so that's a quick overview. A quick overview of the lab 2. So there's some really interesting green building applications out there, and I think all of you being in the construction management field, you're going to encounter at least one of those at some point, if not many, if not most, at some point in your career. But if nothing else, it's good to be aware of them now, and then really think about the overall sort of context here is like the way we design buildings is, it has a really big impact on the environment and on people and society and the economy. And so to really think about how your buildings are doing that, and then think about some practical ways that you can reduce that impact. And also, I mean, frankly, I don't know, I think it's kind of interesting, right? Like, it's nice to not build the same type of buildings all over the place and just sort of slap them up no matter where you are. When you use these design principles, you have to really think about the context, think about how it connects to the rest of the the neighborhood, the rest of the region, and so forth. And you get to use these sort of innovative and novel building techniques and energy generation techniques. So definitely something I hope that you all start, or you keep your eye on, and you think about integrating into your future careers. Okay, so I'll leave it at that. Hopefully this was helpful, and if you have any questions, of course, contact me. I hope one of these days I see more of you in these sessions. But have a great week, and hopefully I'll talk to you all next week.